mean, if you think about the history of some chemotherapy drugs, of aspirin, of cardiovascular drugs, a lot of them have come from plants and the study of plants. So we should really be doing a lot more of this kind of stuff, right?
We can completely change the profile of the plant, and we hope the clinical usefulness just by how we grow it, pick it, blend it, prepare it. I think the phytonutrient world is one which is obviously growing, but is absolutely the future for medicine.
Doctor's Kitchen. Recipes, health, lifestyle.
Carl, thanks so much for joining the pod today, buddy. We've been meaning to do this for a little while, so I'm so glad we finally found the time to do it.
Thanks very much. Glad to be on.
So we met through the clinical entrepreneurship program with the NHS. You've been on it for a little while now. But before that, why don't you talk us through your sort of clinical career and how you got to playing around with watercress so much?
Yeah, sure. So I'm a GP, so I did my medical school training in Birmingham, and while I was doing that, I did an intercalation in medical sciences. So I was investigating carotid body cells from a dissertation and around their ability to sense glucose in different levels of oxygen. So I've always had an interest in sort of the underpinning biochemistry of plants and animals. Finished my training, and then I started an academic foundation training at Torbay Hospital. And I think this was really one of the key things for me, because the academic training post gave me a week every 3 weeks to be able to do quality improvement and research, and that gave me the time to focus on other things. And the way the watercress came about was quite interesting. So I was on a ward round doing a paediatrics rotation, and we saw a really poorly baby who was septic from infected nappy rash. And as I often did, I didn't know what caused nappy rash, and I was interested in understanding the biochemistry. So I went away and had a bit of a read about it, and found that from urine at least, nappy rash is a chemical burn from ammonia. So you've got lots of bugs in the urine and on the skin with an enzyme called the urease enzyme that converts urea to ammonia. So nappy rash, and the same rash that we see in the elderly, is an alkaline chemical burn. And the professor I was working with at the time, he's a biochemist by background. And he was also a physician, an acute physician. So we had a look at whether urease inhibitors had ever been looked at, and we found some evidence that they had been looked at for things like struvite kidney stones. When the urine becomes alkaline, calcium phosphate comes out of solution and crystallizes and makes stones, but they never were very well tolerated. So there's one licensed in the United States, there's never been one licensed in the UK, despite very good evidence that actually urease inhibition could be a novel target. So that then led me to go away in one of these academic weeks off I had and have a look to see whether any plants had historically been seen to have urease inhibiting properties. And they had. So we had chamomile, pomegranate and watercress keep popping up in the literature. So I couldn't find chamomile in the shops. I could find chamomile tea bags, but no fresh chamomile apart from picking it on the side of the road, the big daisies that you see. Went to try and look for pomegranates, and I couldn't really, I could find them, but they were full of seeds, they were expensive, they were seasonal. So I typed into Google watercress company and found the watercress company based in Dorchester. And that's where this kind of last 5-year roller coaster started, really. So I contacted the watercress company. I said, look, I'm really interested in whether we can prove that watercress has got urease inhibitors in, and you never know, it might be a potential treatment down the line, as a really left field punt. But they said, yeah, we'd be happy to work with you on that. So we ended up getting a grant from Torbay Medical Research Fund, who I can't thank enough, and I think there should be a lot more of these charities around, really quick turnaround, gave us some funding. I was introduced to a professor of experimental medicine, Paul Wynyard, at the University of Exeter, and we put together a project. And over about 3 years, with some additional funding from Torbay Medical Research Fund, we proved that watercress had urease inhibitors. So we set up Watercress Research back in August 2019. We took on some more funding, and then we've really progressed from there. So now I share my time from being a GP partner and being someone who dabbles in watercress. And it's been a fantastic journey. So we've we've made a few discoveries along the way. We submitted a patent in December, and it's going really well. I'm sure we'll chat more about the product.
That's amazing. I wanted to rewind slightly because the fact that you found some small studies online about these individual products is quite amazing, and it never fails to surprise me what you can find on PubMed and who actually has the time or the inclination to do these studies that examine the profiles of different products that we otherwise sort of gloss over. I mean, if you think about the history of some chemotherapy drugs, of aspirin, of cardiovascular drugs, a lot of them have come from plants and the study of plants. So we should really be doing a lot more of this kind of stuff, right?
I completely agree. I mean, we're just finishing off our website, so watercressresearch.com will be going live in a couple of months' time, and we've got a full page on the history of medicine and plants. So we've got the chemotherapy agents you talked about, paclitaxel, for example, where that came from in plants. You've got digoxin from foxglove, you've got aspirin from the willow tree, you've got all sorts of other medicines. So when you take a step back and start thinking about it, you think, well, actually, this might not be such an outrageous idea that we might be able to extract something clinically useful from plants. And there are hundreds of other common plants out there with interesting properties, which we're not looking at. And it's not just what's in the plant, it's how you prepare the plant, how you can stress the plant, how you can grow it and cultivate it. We're starting to learn that now with watercress. We can completely change the profile of the plant, and we hope the clinical usefulness just by how we grow it, pick it, blend it, prepare it. So I completely agree with you, and that's why I obviously follow your work greatly. I think that the phytonutrient world is one which is obviously growing, but is absolutely the future for medicine, 100%.
Yeah. It's a really untapped world, I think, and that's why it's so fascinating here about your work on watercress as a single ingredient. And like you said, there's so many different ways in which you can prepare the ingredient that we'll get into a bit later that can yield different profiles, which could have potentially a multivariate uses. Going back to your grant, this is quite interesting for me because the whole grant process is quite is a bit of a maze for a lot of people, and I think if more medics or scientists were actually encouraged and actually saw like a simpler path to investigate different areas of things that they're really intrigued by, we'd have a lot more research like yours. Can you talk us through that whole grant process and why that was so good for you?
So we were really lucky in Torbay to have Torbay Medical Research Fund. So they're not affiliated with they're not part of the hospital, but they're obviously affiliated with it. So the history behind them there were three big law firms in the Bay Area would have people coming to them with legacies and monies to leave to various charities. And with a lot of charities, unfortunately, that money can go into running expensive offices, it can go into wages, and not all the money, should we say, will go to what you think the end use should be. So these three law firms put their heads together and said, why don't we offer people an alternative where we make a charity and it's going to be for the health and benefit of people in and around the Torbay area, and they'll fund research with clear benefit. And you can go on their website and have a look at all the things that have been previously sponsored, and they are absolutely fantastic. So they sit every 3 months. You have to do a 2-page application. And when the panel sits, they'll shortlist you before you're invited to present. You'll present your work, and then you'll be given lots of questions at the time during your presentation, but you get a decision within 2 weeks. And within a couple of weeks after that, the funds are ready. Now, I could have gone down the route of an Innovate UK grant, perhaps, or a Smart grant, or I4I, or one of these grants, but the risk to me at that point in something which has got such a small chance of success wouldn't have been worth me doing. Plus, that sort of a grant, you really need to have experience in grant writing and have a team. And I, at the time, didn't have that. So these smaller pots of money in charities where you can very quickly turn something round as a proof of concept was absolutely invaluable to me, and I wouldn't have been able to get where I am now without those pots of money. And I completely hear what you're saying. As clinicians, our time is limited anyway, and we often don't have all the answers. And I think that's the difficulty with a lot of the grant application processes at the minute, if you're asked about, well, what's the market and what's this, we're not really trained to know about that. We've got an idea and we know the clinical side of things, but asking us, what could projections be and what could other markets be, I think we often find it difficult. So for these proof of concept funds, charities like that and small pots of funds which are relatively easily accessible, I think I'd love to see more of them popping up just for the proof of concept work.
Yeah, definitely. I mean, I just literally done my Innovate UK grant application a couple of months ago, and it is a massive slog. It's like 3 months of pure work. You've got to get everything in order. You've got to do, like you said, projections and financials. And as a clinician, I've been doing a bit of business now for the last couple of years, but still, there's a lot of work, a lot of new learning to do. And like you said, the whole process of bid writing is an art in itself, which is why a lot of people use bid writers, which we didn't do. So, fingers crossed, we'll see what happens with the decision. Cheers. And they're also very competitive as well. You get thousands of people writing for these because they're big pots of money, and rightly so. They're super competitive. So you're at this point where you've got this grant, amazing pot of money, a charitable foundation that makes the decision super quickly, which sounds like a dream come true. And you meet up with this professor of experimental medicine. I don't think people really understand what the process of research is like. So if you've got this idea, looking at some preliminary research about watercress and some properties being urease inhibitors that might be useful in nappy rash, what's the process thereafter?
Well, to be honest, there isn't one. And very much, my last 5 years have been a bit like a pinball machine, bouncing from one place to the other, 2 steps forward, 1 back and 10 to the side. So there wasn't really a process. We kind of had the end goal where we thought, what we wanted to get to at the end of the day was, can we get a liquid or a powder or a whatever form it's going to take with urease inhibitors in, and then can we try it on nappy rash and see if it works? But we didn't know how we're going to get from this stage to that stage. And Paul, who I worked with, he didn't really know either. But I don't think we still know, really. But I mean, I think what we knew is we had to do things in stages. So although you might not know how you get into the end, it's always fairly clear what your next step needs to be. So we realised that what we need to do is we need to figure out how we get these urease inhibitors out of watercress. And we knew they were there because what we did is we spun up watercress, and then we took the sort of tea from it and we put it through a machine which basically separates all the molecules from water-loving to water-hating, so hydrophobic to hydrophilic. And we took various points along that path and we tested them. And of course, some of the fractions were popping up saying these inhibit urease really well, these other fractions don't. So we thought, well, they're definitely in there, but that's not going to be a commercially viable thing to do because it's a really complicated and expensive way, needing university equipment to get them out. So as all good sort of scientists do, we thought, well, let's just blend it up and heat it and see what happens. And see, just because we didn't know. So we thought, we tried everything at that point. So we thought, well, let's just blend it up and then heat it. And this is where we had a bit of a eureka moment, because the watercress, after we blended it up, as soon as it started to steam, it curdled.
Right.
And we thought, well, we've just wrecked a batch of watercress because it's curdled and no one's going to want to eat anything that's all curdled. And then we thought, well, hang on a second, when you're making cheese, the curds are the protein. So we effectively did a bit of cheese making. We poured this hot mixture through a cloth, and then we were left with what looked like a green putty. We sent that off for analysis, and actually it came back to be a fantastic, novel plant protein with really high essential amino acids. So we were scratching our heads thinking, well, we've gone completely the other direction. We set out looking for urease inhibitors, and now we've got a protein, which is great because we've got a byproduct. We then had the liquid that had come through as a kind of brown, murky liquid. And when we tested that for urease inhibiting activity, it was fantastic. So by the sheer fluke of watercress curdling, that's how we figured out how we were going to get these urease inhibitors out. And we now know that watercress curdles because half its calorific value is protein, which is really high. So that's about the same as a ribeye steak. Now, obviously, the steak,
incredible.
Yeah, the steak's got a lot more calories in it. but of the calories available, half are protein. So effectively what we're doing is just coagulating out and denaturing protein in the same way as when you boil an egg, the albumin goes from that snotty, colourless consistency, and it binds together and it coagulates and goes white. So we got quite excited by that, and at that point we took on some private funding from some businessmen in Exeter who were involved who had businesses before, and one of them's in food and drink. And at that point, that's what we needed. So we recognised that we had something that we could kind of see a production process for. But again, we didn't know the first thing about running a business. So we decided at that point, we need to get people in who know how to do accounts, who would know how to do a slide deck, who would know things like that. So that's what we did. So we were quite careful in who we brought in. We brought in 4 guys, and they've been great. So they put in some funding, and they've really helped us to develop this business. And so where we are now is we've got the process, which we've submitted a patent for, to make this liquid urease inhibiting sort of solution. And we've got a way of making this powdered watercress protein, which is sky high in amino acids and fibers and things like that. And the exciting thing for us is we've had some good data back recently, which shows if we put our watercress extract in to a fake urine with Proteus in it. So Proteus is the bug which most commonly causes nappy rash and water infections. It completely eliminates the ammonia production. So we're quite confident that actually we are going to be able to stop nappy rash, and we are close to reaching an agreement with a very big continence care provider for a range of nappies and continence wipes and creams and things like that. So that's going to be our first step. So it looks like we might well have the future of nappy rash all wrapped up, Rupy, which I'm delighted about.
That's amazing. I just want to go back to this process, right? Because I've got this image in my head of you literally using something like a Vitamix to blend up watercress, put it in a big vat over heat, and then literally just heating up at different temperatures and seeing what happens. Was that literally like the process?
So there was absolutely nothing at all scientific about what we did. And the first lesson I learned was put a lid on the pan, because obviously you put the blender on and everything splattered everywhere. So, we learn as we go. The kitchen has been destroyed by watercress on many occasions, but you're absolutely right. We weren't using scientific methods, A, because we couldn't afford to, but B, you don't need to pay a lab to blend something up. We can do it at home. So yeah, we did. We blended things up. And what was interesting about the blending phase, so you take all the watercress, you blend it up, is, as any good scientist would do, maybe not good ones, but it's what we did, is we just kept tasting it at different intervals. So we were obviously used to eating watercress when we were preparing it, and we thought, well, that's peppery. We then realised that when we tasted it, we blend it up and we do something else like clean the kitchen or whatever else, and then we taste it again, and it was a lot more peppery. And we thought, well, that's interesting. So when we started looking at the literature, we realised that watercress is part of a group of plants called the brassicas. So brassica have got things like watercress, mustard seed, wasabi, broccoli, and sprout. So the pepperiness is a plant defence mechanism. So in the brassica family, you've got a group of molecules called glucosinolates. When you blend up the plant, or let's say chew it, then they get acted on by an enzyme called myrosinase, and the myrosinase creates isothiocyanates. And each of the members of the brassica family predominantly produce a different isothiocyanate. So watercress makes phenethyl isothiocyanate, mustard seed makes benzyl isothiocyanate, wasabi makes allyl isothiocyanate. And what's really interesting is they're all being looked at for their various roles in inflammation and the epigenetic regulation of cancers. So looking at the watercress phenethyl isothiocyanate, there's really good evidence. So if you put into Google PEITC and cancer, you'll see all the work that's being done at the minute. So, for example, if there's been studies where they give people synthetic PEITC who are having radiotherapy for breast cancer. And if you supplement people with PEITC, you have a better outcome at the breast cancer from the radiotherapy. Wow. So what the PEITC does is it's able to switch on the death genes or apoptotic genes and switch off the survival genes of the cancer. And what we also see is it exhibits an anti-inflammatory function. So it's got a modulating effect through inflammatory pathways. So the surrounding tissue damage, which you get from radiotherapy, is actually reduced as well. So we, just by blending it up and tasting it, realised that after we blended it up, we're actually disrupting all these cells and converting this glucose nasturtium, which is the precursor to the phenylethyl isothiocyanate, we're converting one to the other. And the reason it's getting more peppery is because this PEITC is just being produced. So
by preparing it in the way you were doing, you were actually increasing the concentration of the isothiocyanate that has all these potential benefits.
Absolutely right. And we figured that out just by tasting it, because the paper said it's the PEITC which gives watercress its pepperiness. So the idea is a cow would come along to a river, chew the watercress, it doesn't like the pepperiness, so it goes on to another plant. So it's effectively like a stress hormone for the plant, but it happens to have all these interesting properties. So we often get asked, well, why do you need to blend it up to make the PEITC? Why can't you get it from chewing? Well, when we blended the watercress, we found that it took 2 hours to convert all the glucosinolates into PEITC. So you probably could do it with chewing, but you're going to have to chew each mouthful for about 2 hours, which I think it would probably blow your head off with the pepperiness by that time. So a complete side route that we're going down now is we've managed to concentrate this PEITC into watercress. So we've got a team in Greece who have been working on some sort of molecular genetics work and sort of cellular mechanisms to look at whether application of our extract into melanoma models could potentially improve treatment or could prevent the incidence of skin cancers. Wow. And they've got various ways of testing that. So this is a completely different thing that we've come across without realizing that we were going to. So from an inflammation perspective, it's interesting. So we're doing some work looking and testing this new anti-inflammatory pathway, because clearly for us in nappy rash, it would be great if we can block ammonia and stop the inflammation. But there's probably already ammonia there anyway, which is going to make some inflammation. Well, if we can show that there might be an anti-inflammatory pathway there as well, then that's a second mechanism.
So you've got dual mechanisms as to how to treat the overall impact of nappy rash. And
that was all just from blending up in the kitchen and tasting it while we were doing other things and realizing there was a change in the taste profile. So we're now looking at different things we can do. So if we were to heat the watercress first of all to denature the myrosinase enzyme, then we can just be left with something which is full of these glucosinolates when we disrupt it, because the enzyme has been inactivated. There are potential benefits for us doing that as well. So we've got 5 or 6 different preparation processes which can completely change the profile of both the flavour but the chemical composition of the extract that we're left with. And similarly, we've got mechanisms where we can retrieve the fibre. Now, watercress fibre, very long chains. You can make plastic out of that fairly easily. So, there's interesting things that we might be able to do with that and with, with a few other things as well. So the more that we're looking at how we can prepare and change the watercress, the more we're realising that actually there's a whole lot, there's a massive potential. So we started out looking at nappy rash. We're now looking at, modulating epigenetics for various cancers. We're looking at whether we can have anti-inflammatory functions. And we now know that, going back to urease inhibition, there are 5 or 6 other conditions out there where urease is implicated. So Helicobacter pylori, which is a bug that lives in the stomach and causes gastric ulcers and bleeds and can cause lymphomas, it survives the acidity of the stomach because on the outside of its cell wall, it's got a urease enzyme. So it effectively covers itself in a blanket of ammonia to buffer the stomach acid. And in papers where you've genetically knocked out the urease genes of an H. pylori, it can't survive in the stomach. So we've been doing some work with the University of Bath. They've got a computer model of the crystalline structure of an H. pylori urease enzyme. And we've shown that our urease inhibitors all dock at different sites and inactivate the enzyme a different way. So whereas with the current urease inhibitors, you've got one molecule. So one of them might be acetohydroxyamic acid. That binds at a particular site. We know that we've got at least 7 urease inhibitors, that some of them bind outside the active site and change the conformational structure. Some of them bind in the active site reversibly and non-reversibly. So we've got a really good spread bet against this urease, which means that we believe we can knock out the urease enzyme. Wow. If we do that, H. pylori dies. So then we're into the territory of, have we made a new antibiotic?
Yeah. I didn't actually realize that you had multiple different ways in which urease is inhibited using the singular product.
Yeah, so we've got 7 inhibitors. Now, what's useful for us is if you look at the urease enzyme, it's relatively well preserved across nature. So some plants have got urease enzymes as well as inhibitors. That urease enzyme is a nickel-based metalloenzyme, so it's got nickel at its core. It's very similar in plants to what it is in Proteus and to what it is in some fungi who've got it as well, and other bacteria. So where we're doing this theoretical docking work with this computer model on an H. pylori urease, that should be very transferable over to other urease enzymes. And the fact that we've got so many different ways of inhibiting it means that transferability, the likelihood is increased. So so the other conditions, apart from H. pylori, we've got struvite kidney stones, some water infections, have something called hepatic encephalopathy, which is where ammonia rises when you've got liver cirrhosis and crosses a blood-brain barrier. All these conditions could be effectively treated. So what we're doing now is we are hopefully going to get a contract for the continent's work. We need to take on some more funding to build a biorefinery. We're then looking to do an application to the Food Standards Agency in the UK and the relevant party in the EU, because this is going to be seen as a novel food. So it's going to be an 18-month application process to get that protein byproduct and the watercress extract registered as a novel food. Once we've done that, we'll be able to start the oral clinical trials, because we'll have all the toxicology studies done, and we'll be able to give it to people who have got H. pylori infections. And we've got some good links with some hospitals in India where it's quite rife, and see if we can actually prove this is a new antibiotic.
This is particularly interesting, I guess, and perhaps you can add some clinical context as to why a substance that impacts H. pylori could be so useful in general practice, where we see a lot of infections with this bug that can lead to gastritis. Yeah,
well, what's interesting with H. pylori is if you look at the prevalence of H. pylori across countries, as the prevalence goes up, you tend to see rates of gastric cancer go up as well. So in places like Colombia, South Korea, the majority of people are colonized with H. pylori. Gastric cancer is in the top 2 or 3 cancers, whereas in the UK it's currently 12th, behind the ones that we would think of common cancers, so lung, colorectal, breast, prostate. So in these other countries, if we can, the dream really is to look at population level dietary supplementation with the urease inhibiting extract that we can make, and we might be able to crash the rates of gastric cancer. In the UK, whereas gastric cancer is only the 12th most common cancer, it's not a very nice cancer to get. It tends to be a particularly horrible one. But we also know that the resistance rates of H. pylori to the various antibiotic regimes that we've got are getting worse, as it is for other conditions as well. Now, because the way we're targeting the urease, and because the urease enzyme is relatively well preserved across nature, we believe it's going to be very difficult for H. pylori to develop resistance to these molecules, because they're acting extracellularly, and it's not going to be able to change the structure of the urease sufficiently to be able to prevent that inhibition, because nature just hasn't done it today. So it might be the case where we don't demonstrate an antibiotic function, but what we do is we make the H. pylori effectively a bit sleepy. and a bit quiescent. So yes, you've still got the bug, but it can just sit in your stomach for decades and not cause you any difficulties. It's the same argument that we have at the minute with urinary tract infections. So you'll know as well, if you looked at, if you took urine samples from 100 women over the age of 80, the vast majority are going to have a positive urine dipstick. Mm-hmm. So because they've got bugs in their urine. But there's a difference between having bacteria in your urine and being asymptomatic to having an infection where those bugs are causing a difficulty. Mm-hmm. And we hope that if we can get through the Food Standards Agency and start a trial taking on this watercress extract, it might not necessarily kill the bugs, but it might just rein them in and sort of get that balance back, that symbiosis, and just, again, make them tolerated better in the gut. So that's what we're looking at the minute. It's going to be a long process. We're looking 2 years down the line just to get this, get the licenses through that we need, and then be allowed to start the clinical trials. But certainly from H. pylori, particularly in other countries, that's a really big one for us if we can get that right.
Yeah, that's huge. I mean, like in the context of antimicrobial resistance as well, which is a growing phenomena. I mean, we had Dame Sally Davies on the podcast a few months ago talking about just how much of an issue this is. If we can find strategies to induce dormancy, like you suggested, of these bugs, or at least render them a little bit less capable such that they're more susceptible to the current suite of antimicrobials that we have at the moment, this is really game-changing stuff.
You're absolutely right. And we know that Proteus, for example, if you knock out its urease enzyme, it doesn't die. But the urease is a virulence factor, so it helps it to survive and colonize areas through various ways, through biofilm formations and through other things. Just by knocking out that virulence factor, I think this is potentially a better strategy than killing off the bugs, having a more of a bacteriostatic effect in just reining them back in, because we're sort of meant to have bugs on us. That's what we're meant to do. And when we give antibiotics and we wipe out half of our gut flora and half of our skin flora, that's not always a very good thing to do. And as you said, the rates of antimicrobial resistance are going up. So fingers crossed, we hope that the watercress extract on its own could have that kind of dormancy effect. But in bugs where you really do want to get rid of them because they're still causing a problem, it may be that knocking out that virulence factor opens the bug up to being susceptible to a wider range of antibiotics, shorter courses of antibiotics, lower doses of antibiotics. And then with that, you'll hopefully get, less chance of resistance, less side effects, less of the diarrhea and vomiting because you've obliterated half your gut microbiome. That's what we're hoping to do. We know, for example, that with wasabi has a particular isothiocyanate called allyl isothiocyanate. Loads of information at the minute being published around the role of allyl isothiocyanate in the disruption of biofilms. So, if you're looking at catheters, for example, who often get blocked and crystallized from biofilms, well, could you use a wasabi and watercress mix? And then what about mustard seed and the sulforaphane from broccoli? They've all got slightly different things. So, we're hoping down the line, could we make a mixture of different brassica families to just have all these different isothiocyanates with all their relative effects as a treatment, which one single molecule isn't going to be able to do synthetically. So for us, and it's that reason that we've got so many different molecules acting that we're never going to be able to make this a synthetic drug, because we think there's benefit in having lots of things working synergistically. So we're always going to be working from watercress down. The difficulty that's going to bring us is if we prove this works fantastically well for, let's say, struvite kidney stones. So we knock out the Proteus urease, the pH of the urine comes down, things don't come out of solution, you don't get struvite kidney stones. The stance of the MHRA at the minute is that they will not license anything which has been extracted from a plant. You have to synthesize it and then demonstrate purity above a certain threshold. So that potentially leaves us with a bit of a problem. I'm hopeful that with the current interest in CBD and extracting direct from the plants, with advances in hydroponic farming, vertical growing, sterile techniques, that stance may change, or there may be, it might not be a true license, but it may be an endorsement. It may be a sort of a sign of acceptability from the MHRA that yes, this can work. And granted, there might be very, very strict growing schedules, but for me, if we can grow things, if we find the perfect watercress plant, because we know there's about 50 species, and we're going to spend some time splicing and chopping and changing watercress to get the right species. But if we can prove, you take this species and you grow it for this amount in this water, this pH, all the rest of it, and then we can harvest it and time after time demonstrate purity above a certain threshold, I'm hopeful that's going to be seen as acceptable, and then we might be able to start licensing it as a medicine.
Yeah, that's literally what I was going to suggest there. Actually, we did a podcast series on CBD with an anaesthetist that uses it for pain medication, and one of the the thought leaders who's actually campaigning to the MHRA about the uses of CBD. And it appears that it's the entourage effect of the compounds in the plant rather than the singular element of CBD itself, which sort of stands to reason as to why the MHRA are going to have to change their thinking about this from the traditional model of pharmaceuticals, which are singular components that are, purified to a certain amount, to a more holistic approach of how we use these plant compounds, because it's not going to be one thing, it's going to be a multitude of different things. Going back to the solution that you were talking about, did you have an inclination as to whether this was going to be a topical product versus an orally ingested product for nappy rash, or are there multiple uses depending on the way you apply it?
So we started out looking at the topical route purely because we were aware that the Food Standards Agency weren't going to let us give anything orally until this was signed off as a novel food. So we knew that process was going to take 18 months if it was quick, but potentially 2 years. And for us as a new business, we kind of needed to start generating funds before that so that we can attract venture capitalist funding, get biorefineries up and running. So the topical route does carry less regulations. And actually there are some really good companies out there that we've been working with who can test topical products for inflammation. So we work with a company called LabSkin. So LabSkin have got an in vitro cell model. So they grow fibroblasts, so new skin cells on a mesh. And cosmetic companies are using them instead of animal testing now, which is absolutely fantastic. And we did exactly the same. So we put our watercress extract on the LabSkin, and we demonstrated that we didn't cause an inflammatory effect on the skin. And we then undertook a clinical trial with patch testing and showed that actually there is no inflammation that's caused by the extract, so it's safe for skin, and there's all these other things that we can say. That process was a lot quicker than having to go down the oral route. We do want to go down the oral route, but going topically is certainly easier to begin with. And actually there's sort of something quite nice about this now coming full circle back to nappy rash, when they start from being on a ward round and seeing the poorly baby with nappy rash. It feels nice that we're going down that route. But in time, if we can have a nice range of continence products with the PEITC and some of the other molecules that are seen as being anti-inflammatory, we have to wonder about other pro-inflammatory skin conditions, eczema, psoriasis, other forms of dermatitis. Particularly, people are using so much alcohol hand gel at the minute. There's loads of people out there with dry and cracked skin. Well, could we put a watercress extract in the alcohol? Could we have a cream? Yeah, exactly. The constant exposure to soap. So we're certainly going to explore that route. That's going to give us the ability to then set up the biorefinery with the rigs that we need to go through our production process and filter it down to something which is sterile. And then we'll be able to do the Food Standards Agency. And actually, there's quite a bit of agricultural interest in this as well. So farmers have been using urease inhibitors for a long time. So urease inhibitors help plants to hold on to available nitrogen. So we might be able to offer that naturally as an organic solution to help organic crops grow. And we're kind of hopeful it might work as a bit of a sports supplement as well. So in the gut, if you stop urea to ammonia, the urea can be cycled into other useful amino acids and absorbed. So a big market for us when we do get sign-off is to look at sports supplement, yes, but frailty and age-related muscle loss. So where we give people lots of build-up drinks with loads of calories, loads of protein, actually not much of that protein is absorbed. Well, if you can improve the efficiency of the gut rather than just filling people with protein, that might be a better way of doing it. So yeah, lots going on at the minute there.
Amazing, mate. That's so cool. You know the curd that you were talking about. So the through the cheesecloth, and you have this lumpy sort of curdled material. What's the protein profile of that, and what does it taste like?
So it tastes. So when people ask me that, I always have to give a bit of an odd answer. Have you ever chewed grass before? Just like normal grass in the field.
Probably as a kid.
Yeah.
But not recently.
So I don't know. As soon as I tasted the putty, I said, "Oh, it tastes like grass." And then people would ask me, "Why have you spent time chewing grass?" And I don't really know how or when or where I was chewing grass, but I certainly have, and that's kind of what it tastes like. So, you know, it's an interesting byproduct because it's got a relatively neutral flavour. All that kind of pepperiness, because that's in the liquid, comes out in the liquid. So there's a little bit of it in the putty. So, you know, we're interested in what we can do with it because it does have a nice putty texture. So when you chew it, if you kind of ignore the flavour, it does feel a bit meaty because it has got fibre. So it does have a bit of resistance there. So we might be able to put it into meats as a bit of a meat substitute. It seems to stay bright green, which is quite nice. And in terms of the protein profile, so I think 33.8%, I think it was fibre, 39.8% was protein, and the rest of it was all just useful vitamins, minerals, low sugar, you know, low salt, low fat, as you'd expect from a plant protein. So
39% that's really high.
And what's interesting is that's just with it being curdled and boiled off. We can skim up the watercress and then put it through a coarse filter, then heat it, which means we'll get a pure protein isolate. So if we can take off a load of that protein, we can probably get the protein content of the curds to over 50%. So we sent that off to Camden BRI, they sent it back, the amino acid contents, and it looks like the essential amino acid content is higher than any individual plant protein that's out there at the minute. So your pea, potato, your soy, and all these ones, yeah, it's really high. And again, the essential amino acid profile looks more like an animal protein. So, you know, we hope that for vegans and vegetarians, this might offer an alternative, nutritionally complete protein source. And again, you know, what we want to really do is a program over 2 or 3 years looking at, you know, how we harvest the watercress and how that makes a difference. What about the mixing? What about the temperatures? The interesting thing about the curdling is if we can figure out a way, which I think we have done, of getting the protein out in its native form, it could be really useful in things like bread making and in other cooking because of that ability to bind. So at the minute, people use egg whites for the same reason. You mix things up. Yeah. You know, when you heat the egg white, it sort of pulls everything towards it. And, you know, it might just be that this protein can offer that function through a different way. And the functionality of proteins is something that we've become really interested in. So there's all sorts of things that companies look for, you know, in terms of gelling function, ability to hold on to water, as well as the things that we'd often think about, the taste and the and what it feels like in the mouth, that kind of organoleptic thing. But you know, the function of proteins is interesting. So, you know, hopefully we can come up with a process which is relatively easy to do with the equipment that we're going to be getting, and then we can offer something. So, you know, I know there's a companies who make mycoprotein and things like that. It's inherently very crumbly, and a lot of the time egg white is used to bind that together. Well, from a vegan perspective, you can't, you don't really want that, and the crumbly protein, it's sometimes difficult to work with it. Whereas if we can bind it together enough to make it useful, well, then you open up not just the watercress protein, but all the things it can bind in to that vegan market and make it make it more readily available. And, you know, that's the route we need to go down. I mean, plant proteins in a plant-based diet, the amount of literature coming at the minute is fantastic. And, you know, I can put this sort of protein curd in front of people and say, well, look, this has got the same amount of protein as this chunk of ribeye steak. but now there's less. There's no fat, there's no sugar, there's none of the other issues around it. The plant protein market is really interesting, and particularly the functionality of proteins in both their sort of natural form and also in their denatured form. So it's something else that we're really excited to be looking at.
Yeah, definitely. I mean, I was at the Future Food Laboratory event a couple of years ago now. It was pre-pandemic, and it was basically like a B2B event with investors and VCs and all the rest of it. And the dominant talk was all about plant proteins, and they talked about soy, they talked about mycoproteins, various others like, Impossible Burger, etc. But this is quite an interesting field because I'm just thinking of this putty and the ways in which you can dehydrate it, powder it, put it into shakes, build-ups. You can combine it with other novel protein sources as well, like the soy and tempeh, to make it still vegan. And like you said, if it has as a textural component that actually improves the palatability of a patty or something like that, then that there's some real novel uses in food.
Yeah, there is. And the difficulty we've got at the minute is if we wanted to make some extract now and some protein, it costs us thousands of pounds to rent out the lab up in the north of England that we've been using to create it. Whereas once we've got our biorefinery up and running, we can be making lots and lots of different samples and sending them to these companies. Now, for ease at the minute, it's going to be far easier for us to powder down the putty because we can store it. If we keep it as a putty, I think the likelihood is we're going to have a cold chain. So it's going to have to be refrigerated, and then the clock's ticking as to how long you've got before you can sell it. I'm not saying it's impossible, but for us, again, thinking about what's the next step and what's the easiest thing to do, powder's got to be there. And, if you have a bowl of mashed potato and then you mix in a load of this powder, you can hugely increase the protein content, the vitamin profile. So you're absolutely right. For soups and shakes and things like that, something which is easily mixable, neutral flavour, it's going to turn everything bright green, but I don't think that's necessarily the worst thing. It could work. It could work really well. And then once we're up and running, we're established, we can start hopefully working with maybe sausage manufacturers or other people and say, well, look, what about replacing 30% of the meat in the sausage with this watercress? And then you get it's going to have the same flavour because it's got the chewiness, but the same texture because of the chewiness, and you might have a bit of a pepperiness, which in sausages might be quite nice, and we can just start exploring that market. So for us, we sort of try and understand one bit of it, and then three other things open up that we've got to try and understand, and we just kind of cautiously take a step forward in each way. But you're absolutely right. The protein market is really interesting, and for us, having this as a byproduct is great. Because we can sell it at a much lower price, because really the main business of what we're going to be doing is selling this PEITC rich urease inhibiting extract and doing all the underpinning plant science around that. Yeah.
It's incredible that, most people think about watercress and just think of this beautiful leafy ingredient, and you wouldn't have thought that, if you process it in a certain way, you'll get this really high protein isolate. And I guess the other thing about watercress that I put it in a whole bunch of different things, because it's got lutein. It's one of the best sources of lutein, which is great for eye health, and all the different phytonutrients like apigenins and camphorol, and as well as all the glucosinolates that you just mentioned. One thing that I've come across is its potential impact on environmental pollutants. Is that something that you've come across yourself, and whether that's another market, considering how urbanized environments are having a detrimental effect on human health?
So the environmental impact of the watercress that we've been looking at, there's a few parts to it. The first thing which is interesting is we're able to use the watercress that the watercress company have as their insurance policy. So the way it works at the minute is they've got a contract with, let's say, Waitrose. They have to meet that quota. Now, one of their fields in Spain or Florida or the UK might get knocked out by an adverse climate, or machinery might go wrong and they can't harvest, so they have to overproduce by up to a third just to make sure they meet that demand. The rest of the watercress often is then just sat in the field, doesn't do anything, and then it has to get replaced by the new watercress, because if you leave it for too long, it then flowers and people don't want to eat the flowering watercress. So we're able to come along and take something which has got a shelf life of 7 days after it's been cut and turn it into something which has got a much longer shelf life. So we know that our liquid extract has got a 3-month shelf life at least, because we just tried it after 3 months and it was exactly the same. The powder, we imagine, would be similar, if not longer. So I think one of the things which is nice about this is that we are able to take what is effectively the waste excess plant and turn it into something useful. And when you start looking at vegetable farming across the board, there are so many instances where farmers are having to overproduce just to meet quotas, and there isn't really a plan for that excess. At the minute, for the watercress company, it sort of gets put into a vat, it gets rotted down into a tea, and farmers can use it on their fields. But this is just something which offers another business to it. So I think we're interested in that from the environmental perspective. I think the other part of the environment, not so much around the urban side of things, which you mentioned, but is around fertilizers. So urea fertilizers are really going out of fashion. And the reason they're going out of fashion is because of the ammonia that they produce. And, if we can demonstrate that we can stabilize the urea with this watercress extract, then it might well be we can reduce the environmental impact of ammonia. And, we hear all the time about the impact of methane from cows and livestock. The impact from ammonia is absolutely massive, because it has a tendency to, whereas methane will go into the atmosphere, the ammonia tends to leach into streams and raise the pH. That can absolutely obliterate the biodiversity in streams and lakes and rivers and cause algal blooms and kill off a lot of the wildlife. So I think from an organic growing perspective, which I think people would agree is the direction we want to travel, we have to find natural alternatives or fertilizers or whatever it might be to replace these synthetic ones. And we're hopeful that the watercress extract is going to be able to do that. So along with the topical stuff we're doing, the food and drink, the medicine, we've got 3 studies at the minute looking at the impact in soil ammonia production when you put the watercress extract on it. So I think that's what we're interested in from the environmental perspective.
Is there any evidence around the ingredients in watercress that protect humans from environmental pollutants by upregulating certain enzymes in the liver, like detoxification enzymes like superoxide oxide dismutase or glutathione, for example?
Oh, it's probably the thing I didn't look at before I came on here. That's
Oh, don't worry about it. That's fine. I was just wondering, because the only reason why I ask is because I'm aware of a few studies looking at sulforaphane specifically, and the ability of sulforaphane when taken in extract form to excrete benzene. There was a really interesting research paper that I'll link to in the show notes, and I'll send it to you as well, where it was performed in China and Beijing, so very heavily polluted area, and they found that this sulforaphane extract, when taken daily, increased the excretion of benzene via urine. Exactly. Yeah, so
absolutely no doubt you're going to be right. I mean, we come across so much at the minute. It's becoming difficult for us to keep track of absolutely everything that's going on. Someone will come across with a paper and say, "Oh, did you know that this molecule in watercress has now been shown to do this in the spleen?" And we go, "Oh, well, that's great," but it's another headache for us, because how do we manage it? So it's a fantastic problem to have. Thanks for bringing that up. It'll be I'll certainly have a look at that. There's just so much that we seem to be able to do with just watercress and then the brassica family, and we're quite excited to start looking at other plants and things in the future as well. It's an exciting thing to do.
Well, this is what I was going to say, because you mentioned a couple others like mustard seed, wasabi, all these things that we actually grow here in the UK as well. I think the wasabi farm is like in secret because it's such a valuable ingredient. But, it just strikes me as surprising that we haven't really thought about this kind of research before, and B, just the number of different avenues you could take this in medicine, because as we know, synthetic medications, as they as incredible as they are, as the fact that, we use them daily, amazing ingredients, but they do have limitations. And it seems like we need to think laterally about other ways in which we can improve people's health, and using natural compounds seems to be the way to go.
Yeah, you're absolutely right. I mean, there's an interesting thing about wasabi. So if you look at the sushi packs that you get in the shops, and they've got the wasabi packet, it's not wasabi. It's green mustard seed, because the allyl isothiocyanate often degrades, so it doesn't retain its pepperiness, and it's quite an expensive ingredient anyway. So if you look on the back, it's green food colouring and mustard seed. So, there's all sorts of ways that we might be able to disrupt that production, that wasabi production of allyl isothiocyanate, to then actually preserve it until the point it's on someone's plate in a pack. So it's one of the things that we're looking at as well. But you're right, there's all sorts of things that we can do. And I think it's, I don't think there's enough people actually really, getting interested in plants and the plant science behind it. It's really interesting for us. So not quite sure what the next 5 years are gonna show, but it's gonna be interesting.
Yeah, no, definitely. I did a little bit of research before coming on and looking at the rise in the medical food market over the last 5 years, and how you're seeing sort of acquisitions by big companies like Nestle in particular, and Unilever and a whole bunch of others acquiring smart food and functional food companies, because they definitely see the trend earlier than us population, us lay people. I think this is going to become a lot more common. It's just so fascinating that you're doing this with watercress, with an ingredient that is ubiquitous for health and flavor, and the way we can use it in food, but just putting it in a completely different context in real medicine. It's brilliant, man.
Yeah, no, thanks very much. As I say, there's lots of hurdles that we're going to have. We think the next couple of years are going to be really exciting, particularly if we can get this signed off as something which is safe for consumption, because automatically that opens up the food and drink market for us. And as the company registering the novel food, we get a 5-year license as the only company who's able to produce it. So, we're hopeful that one of the companies, your Nestle's, your Coca-Cola's, your Pepsi's, your whoever else, will come along to us and say, well, this could be really interesting as a functional food, or just as something a bit different with a peppery flavour. And then, of course, as soon as we've got that sign-off, we've got teams ready across various medical specialties to do the clinical trials. And my job really is to try and coordinate everything and start that discussion fairly soon with the MHRA to understand how can we get this through. And it's going to be easier once we've had a few years under our belt doing some of the plant science. So, we know that the glucosinolates in watercress are more commonly found, or there's higher concentrations in the flowers and in the seeds. Now, if you're going to eat watercress, it's harvested before it flowers. So, when we go back to the waste, that flowering watercress, which isn't used because it's the insurance policy, well, that might be a great way for us to increase our glucosinolate and our PEITC level by taking a top cut of 4 inches, getting lots of the flowers and the seeds, and then having that production process in place to maximize it and say to the MHRA, look, we're doing absolutely everything that we can to maximize the concentrations of these bioactive compounds, and we just need to get that discussion going with them. And whatever happens, I'm just going to keep knocking on the door until we make some progress. So hopefully I'll be a bit of a headache for them, but I think we have to move into looking at plants. There's so much potential. I mean, we're struggling to keep on top of everything because of all the different avenues that we found. We started out in nappy rash. We're now looking at food and drink. We're looking at new proteins. We're looking at, can we make plastics? There's other things we think we can do with meat curing and athlete's foot, all just through good science. And I think one of the other things which is really interesting about all this is taking clinicians and putting them into universities and other institutes where they can speak to researchers and speak to biochemists. So Paul and I have got an absolutely fantastic relationship. He's a biochemist, and he'll often come to me and say, oh, we've got this, fantastic new PhD student in who's doing a project, and they can tell us all these different sorts of basophils, and it's going to be great for medicine. And I say, well, that's not something that we use at all. And then as an off-the-cuff comment, they say, oh, and we figured out a new way of measuring glucose with a finger prick. just, or HbA1c with a finger prick and it can do this, and he'll say, it's a bit boring. And I'll say, well, hang on a second, this is really interesting, so, and I think that's what I'm really keen to try and encourage, getting clinicians who've got the clinical knowledge, pinning them to people who've got engineering backgrounds, who've got biochemistry backgrounds, plant science backgrounds, and just get people sort of chatting. Getting people who are interested in new ideas, just discussing, and the amount of things which could come out of those discussions are fantastic. And that's how Paul and I, we've got a little black book of ideas, and if Watercress, eventually does come to an end for whatever reason, there's 4 or 5 different plant-based things that we're looking forward to working on. I just wish we could get more people talking about it, really.
Definitely, mate. I like, as you're talking, all I want you to do is to create a company that everyone can invest in and just throw money at, and then you can spin out different companies thereafter, because I think it would be one of the best investments that anyone could make.
Unfortunately, if I distract myself from Watercress anymore, my shareholders are going to shoot me. So I'm going to have to do that down the line, but I'll know where to come for the future.